Hello, Gregory Carlson here with the Calculus Building, and we're going to talk now about limits at infinity. And so everything we've done so far has been limits at a point, where the left-hand limit and the right-hand limit hit the same point, and that's a limit at that point. What does x approach? And so now what we're going to talk about is a kind of different kind of limit, and that's a limit at infinity. And we're going to start with this question right here. Imagine I have the fraction a half. Okay, so just 1/2. And then let's say that I add a fourth to it. In other words, I add half of a half. Okay? And then we're going to add half of that, so an eighth. And so on and so on. So plus a 16th, plus 1 over 32, plus 1 over 64, forever and ever and ever and ever. So the question is, what will this equal? If we add up this infinite series of fractions, this infinite sequence of fractions, what is it going to equal? And your first instinct should be, well, it's got to equal infinity, right? Because, I mean, you're adding forever, and so it's got to be infinity. There's just no other way around it. But it turns out that calculus isn't always so straightforward. You'll remember that even though we were approaching the door forever, we never reached the door. And in fact, even though we're adding here forever, we're actually going to converge at a number. Let me rewrite the sequence so you can see. This would be the sequence 1 divided by 2 to the I. And we're going to sum it, this is the summation, from 1 to infinity. Okay, so hopefully you're familiar with this notation, 1 over 2 to the I. If I do 1, 2, 3, 4, 5, 6, 7 for I, that's going to be this sequence right here. And so we've got infinity on top of the summation sign, so that's a little strange. So instead of doing that, let's replace it with an n. We're going to replace it with the letter n. And then what I'm going to do is I'm going to let the limit as n go to infinity. So you can see that this is kind of a limit now. We have the limit as n goes to infinity of summing 1 to n of 1 over 2 to the I. So here's what the answer is. I'm going to show you. It starts with a box. There we go. And so what I'm going to start with is my first fraction, and you see that I have half of a box. So I have half of a box, so I'm going to fill in this half. And I think you'll agree with me that so far I have half of a box. All right, let's add the next fraction. That's a fourth. So after 2 steps, you can see that we've filled in 3/4 of the box. We have 0.75 or 3/4 filled in. Next, let's add an eighth. And an eighth is half of a fourth. Then we'll add a 16th, and a 16th is half of an eighth. So that's half of this. And we can keep going. Do you see where we're going with this? Add a 32nd, add a 64th, add 128th, 256th, 512th, 1024th. And so I'll never fill in this box completely because I still have a little hole right here. But do you see that as I add more and more and more fractions, this box is going to get fuller and fuller and fuller? In fact, this limit is equal to 1. So this infinite sum is equal to 1 full box. After you add in an infinite number of decreasing boxes, the limit that that amount will approach is equal to 1. So I think that's just a wonderful little demonstration right there. So let's look at some limits to infinity of actual functions now. And by the way, what we just saw in that converging, that's not always going to happen. You're going to learn more about that actually in Calculus 2. And it's not always going to converge. Oftentimes it diverges, meaning going off to infinity. We just got lucky that these fractions over here were getting small enough, fast enough, so in order to allow it to converge. All right, let's look at this example. Let's look at the limits to infinity of this. We have the function 1 over x plus 5, which you should recognize as a hyperbola, and you should know how to graph this. So because y will never equal 0, 1 over x will never equal 0, y will never equal 5. So our horizontal asymptote is at 5. And again, you should have learned how to do this in the Algebra 2 building. There we go, and we also have a vertical asymptote at 0. And so let's graph this. This is just going to be a sketch. I should have a point right here on the hyperbola and one point right here. And since it's just a regular 1 over x, we have it getting steeper and steeper, but never crossing the asymptote. And we also have one down here. So there's a rough sketch of what the graph of this hyperbola looks like. The +5 bumps it up 5 spaces. So what is the behavior as x goes to positive infinity? Well, as x goes to a positive infinity, this path right here approaches the horizontal asymptote. And so that's going to actually converge to 5. So as x goes to infinity, we're going, getting closer and closer and closer, never equaling 5, but that's the limit that we're approaching. This should say negative infinity. What would the limit be as x approaches negative infinity? Well, now we're on this branch and we're going this way. And as you can see, it's actually, although we're approaching it from the bottom this time, it's going to equal the same number. It's going to equal 5. Let's look at this is what's called the end behavior, by the way, the end behavior of the function. Hopefully you know what the graph of x squared looks like. If it's just y equals x squared, we have a 0, 0 vertex. And then it's up 1, 4, 9, and so on. And same over here, up 1, 4, 9, and so on. So what's the limit as x goes to infinity? Well, as x gets bigger, as x goes to infinity, you can see that it's going to go up forever. It's going to keep going up and up and up and up and up. So that limit's equal to infinity. How about as x goes to negative infinity? Same story. It's going to go up forever. So as x goes to negative infinity, we're going up in both ways. So both limits, both end behaviors are infinity. How about y equals x to the 3? What are those limits going to be? Well, hopefully you know that y equals x to the 3 looks like this. X to the 3 does have a negative part. X squared is all positive, but x to the 3 can get negative. So let's see, as the limit as x goes to infinity, same with the parabola. We're going up, 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 up. So that limit is positive infinity. And you should maybe put pluses here. I mean, technically, infinity is assumed to be positive without a sign, but just to be safe, we should put a plus there. How about as x goes to negative infinity? So as we move in this direction, we're moving down, 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 down. So that's going to be negative infinity. So you can see that x squared is a little different than x to the 3rd. As we're going down, that end limit is negative infinity. How about the square root of x? Well, hopefully you know that the graph of the square root of x starts at the origin, and it goes over 1, up 1, over 4, up 2, 9, 3 is on the graph, and so on. So there's the graph. What are the limits? Well, the limit for this as we go to the positive infinity, although it gets flatter and flatter and flatter, it's going to go up and up and up and up forever. So positive infinity is that limit. What about the limit as x goes to negative infinity? Well, that's a problem because we don't have graph over here. This is where the square root is negative, and so it's not real, it's imaginary. And so there's no graph over here, so this question doesn't really make sense. So what I'm going to say is that the limit does not exist. And the reason the limit does not exist is because the graph doesn't exist going towards negative infinity. So that question doesn't make a lot of sense. What we can say, however, is what is the limit as x goes to 0? So if you look here, we see that the graph approaches 0, approaches 0, approaches 0, and it looks like it's approaching the origin. And it turns out that the limit as x approaches 0, y also goes to 0. So that limit would equal 0. Remember, it doesn't matter that that origin is actually on the graph. I mean, it just so happens that the square root of 0 is 0, but we're approaching 0. That's what's important. Let's look at one more example, and this one's a lot of fun. This is what f of x equals the sine of x. Now, you should remember from the trigonometry building that sine of x goes through the origin. And then if we're doing radians, then it goes up to 1. And then at pi, it hits the origin again. And then at 2 pi, hits the origin again. And then at 3 pi. So the right side of the graph kind of looks like this. And the left side, same thing. At negative pi, we hit 0. Negative 2 pi, we hit 0. So here we go. So there's your graph of sine of x, just waving a nice little wave graph. So what do you think the limit is as x goes to infinity? Well, obviously the graph goes, and eventually it's going to hit the origin. But then it's going to go down and be negative. Okay, but well, then it's going to go back up and become positive. It's just going to keep being a wave forever. And so what would the limit be as x goes to infinity? You can't prove that it's going to land on any one of those numbers as it bounces up and down and up and down. So it turns out the limit as we go to infinity does not exist. It's just going to keep bouncing up and down between 1 and -1 forever. And so likewise, as we go to negative infinity, it's just going to keep bouncing up and down and up and down. So that limit does not exist. So I hope you now have a good understanding of limits at infinity. Next, we're going to do limits of piecewise functions, and I will see you there.